Welcome everyone to the 2024 January Meetup. Start of a new year, so thank you all for being here. Really looking forward to this year's lineup. Nice bunch of things we got going. Gonna be a nice fun year of talks. So the very first thing we always do, it's a little harder nowadays with the economic outlook it looks like, but if anyone's hiring, let us know. Is anyone in the room hiring? Not anymore, man. We used to have like 5, 6 people raise their hands. Stop laying off people and hire people. All right, so if no one's hiring in the room, if anyone watching virtually is hiring, you can go to the nyhackr Slack, and we'll post that in the chat room, in the YouTube chat. And there's a channel called Job Postings. You can post jobs there. People can apply for them. Someone applied just in the past few days. Someone put up a link in the past few days. I hope people applied. So if you want a job, go to the job posting section of the nyhackr Slack. If you don't know where that Slack is, go to nyhackr.org. There's a link for it. It used to be pretty hidden, but we made it less obscure. So for those of you in the room, those of you virtual, you're going to be left out for a moment. Those of you in the room, the pizza today came from Village Square Pizza. I want everyone to take out their phones, those of you who are repeats know the routine, and go to bit.ly/pizzapoll. bit.ly/pizzapoll, all lowercase, and there's going to be a 5-point scale for you to rank how you like this pizza. Let us know how it is, and then as you're voting, they tell you the backstory. It's alleged that this is the same recipe that is used at Prince Street Pizza, which is a really famous place. In fact, it's actually the site of the first ever original Famous Rays. Right, so this is Village Square, which is supposedly a copycat recipe. I don't know, I'm not getting into that. But hope if you enjoyed it, if you didn't enjoy it, go vote. Some of you didn't take out your phones. You should be voting. Looking at you, right? I could shame you into voting, right? Those of you that are watching from home, go into the chat, either the monthly meetup chat of the Slack or of the YouTube channel, and let us know what you're eating. If you're eating pizza, let us know where it's from. If you're eating noodles, tell us where it's from. If you have a beverage, let us know. We're all looking to have a fun time eating together. If you can't be here in person, at least hopefully you're enjoying something far away. And actually, I know there's virtual people watching from down the street. I saw some people sign up who went to NYU, and we're at NYU right now. So, if you can't be here, you can't be here. Another news about another event we have coming up. This year is the 10th anniversary of the New York R Conference. We're really excited. It's been 10 years of this, and it's actually the 15th year of this meetup. So we're going to have a nice big celebration as part of the conference. It is May 16th through 17th. So May 16th through 17th, we send out a save the date. We have not gone live yet with ticket sales. When we do go live, you can use code NYHackR for a 20% discount. And there's also going to be workshops to be announced very shortly. So that's coming up in just a few months, May 16th through 17th, 10th anniversary of NYR, 15th anniversary of this meetup. So we're really excited about this. We have a great lineup coming. We have a bunch of the old guard of the R community coming, some of the new guard, a mixture of people. It's going to be a lot of fun. And for the people attending today, both in the room and virtually, we will draw a name at random to give away a free ticket to the event. And that free ticket can be used either virtually or in person, as you see fit. And speaking of speakers, the meetup group needs more speakers. All right? Every few months, sometimes we have this thing planned 6 months in advance. Sometimes we have it planned 3 weeks in advance. Right now, we're in the 5-week in advance phase. So if anyone in this room hasn't given a talk, raise your hand and say you're going to give a talk. Oh, I saw it. You raised your hand? No. All right, seriously, I won't pressure you. If you want to give a talk, if you're a virtual speaker person, you're going to be passing through New York. You want to give a talk? Let us know. All you have to do is send me an email, Slack me, find me on Twitter, get in touch with any of us. We are here and eager to have people give talks. That's how this month's speaker, I asked, does anyone want to give a talk? He emailed me within like 3 minutes and said he'll give a talk. So we need more people like that. Come give talks. Don't make me chase you. Some of you have been chasing for a while, and you're going to have to pay the piper soon. All right? But anyone else, just let me know when you want to give a talk. All right? It's really easy. And that goes, if you don't want to give a talk in February, by the way, we also have slots in March and April available. May is full already, believe it or not, but that's the way it works sometimes. So, after the meetup, after the talk, for the people in the room, sorry folks virtual, we are going to go to the bar and have a few beverages. If you don't drink alcohol, have a soda or a water or whatever. Just come hang out with us. We have it narrowed down to 2 bars, Vol Denis and the Half Pint. And George is going to pick the winner.
Half Pint.
We're going to the Half Pint. All right? So after the talk, we're going to the Half Pint. If you don't know where it is, you have Google Maps. If that doesn't work, you'll follow one of us there. Okay? So, lots of exciting things. Hope everyone is going to post jobs on the job channel. Hope everyone's enjoying their food, whether in person or virtually. We have the New York R Conference coming up May 16th or 17th, and we need speakers, and we're going to the bar. Sound good to everybody? All right, well, welcome to 2024. Hope everyone has a start to a great new year, and we're looking forward to a whole bunch of good meetups. So with that, I'm very excited to introduce our speaker who volunteered to speak. Right? I want more volunteers. Going to give what I'm sure it's already looking like to be an exciting talk, though you apparently gave this in October 2023, so we need a time machine. So someone had to call you out. It might as well have been me, so everyone can see it. So with that, everyone please welcome Vikram.
Thank you, Jared. Thank you all for being here. You didn't have to call me out on that because I knew this as soon as I was writing this, and I wanted to retain it for a reason. So this talk is based on a talk that I had given at NYU for a bunch of students and researchers on the practical side of machine learning. For myself, I wanted to know what has changed in the slides since I made it in October 2023 to where it is right now. So thank you for calling it out anyway. So there are three quote-unquote phases to this talk, or three portions to this talk. The first is some of the thinking traps in machine learning. I'm going to go through a quick sketch of how commonly machine learning is thought of and how people argue about it, implement them, and so on and so forth, and some of the thinking traps involved in that. The second part of the talk is essentially on how one can use structures and perspectives to perhaps not fall into some of those traps. And it's not that those traps are dangerous, quote unquote. It's just that those traps are avoidable if we put in a little bit of foresight and thought into what exactly is it that we're building. And the final part of the talk is an example of an engineered solution that allows us to kind of remediate and look and have a perspective where one doesn't invariably slide into those mental thinking traps. Anyway, to get started off, we have a question. This is something I ran in person when I did the talk at NYU. What is the ratio of machine learning code to non-ML code in any application that one could think of, or in an application that one is intending to deploy ML? So here's a QR code for that. If you guys could pull up your phones and point at them. And I believe you can also go to this URL. I'm not sure whether that URL is visible. All right, and I'll give us all a minute just to respond to it. There are three choices in there. Yeah, take your best guess at what you think is the proportion of ML code to non-ML code. We'll continue on. That survey is interesting to us just to see how people react differently before and somewhere midway through the conversation. So typically, what does machine learning involve, or what is machine learning does machine learning entail, right? If you ask anyone, almost everyone, people would most likely say, pick a model, all right, let's do that, and train them, all right, let's do that, and then deploy them. So at least we have come to a phase in contemporary conversation where we've recognized that there are three different phases, and they have distinct phases that one needs to go through. And at the end of these, we would have deployed machine learning. And our system, which was without a machine learning model previously, now is capable of using a machine learning model, and we're done. So obviously, that's not the case. We don't go home. There's something missing here in this thinking. And in order to emphasize that, or at least illustrate part of what that is, what is the disconnect between what we think typically versus what is truly involved in, I've laid out something along the lines of what might be conceived of a typical architecture of an application. And down at the bottom, I have something in yellow highlighted that is disembodied perspective. And you may see some of these recur in some of the slides. That kind of helps drive home some of the thinking traps. So here we have users on the way on the left. There's a web tier somewhere next to that, and then we have these microservices or the app tier, bunch of caches and queues and so on, and then there is the data storage and files far on the right. This would be a regular stack of application. There are many ways to slice and dice them. There are many different architectures of applications. Probably people know of MVC models and related families of models, models as in techniques of architecturing applications. But way on the side, down at the bottom, is the ML model standing aloof by itself on the side. And this is what I call the disembodied perspective. And this is what we generally carry with in our minds. And obviously, the argument here is that is not the case. So let's look at how one conceives of the flow of machine learning within an organization. In the sense, we actually spoke about the three phases: pick a model, train the model, and deploy it. And essentially here, what I'm highlighting is that itself, horizontally laid out, but we're embellishing it with a few metrics down at the bottom and saying, all right, I have at the end of having created a model, validated it and tested it, I look at the metrics and say, okay, my metrics look great. Now it is, and here I'm showing something known as a classification area under the curve, and it's greater than 50%, and that is indicative of this model now being ready to be deployed into our live system. But again, let's say we did that. What typically would happen is something along the lines of what you see in the goal metrics on the right-hand side. You may have an initial bump or a boost in your goal metric. And then you would see a gradual deterioration in your goal metric over time. And especially this is quite relevant in the case of online settings and online service settings, where we have what is known as contextual decisions being made. A user repeatedly interacts with the system. You go to YouTube, let's say you're shown a video to watch, and then you interact with it, choose not to watch it or watch it, and then you're given another recommendation and so on. What would initially happen is for the first few weeks, the first few days that you deploy a specific machine learning model, you would see a little bit of bump in the goal metric that you're looking at. And then after a week or two or so, you would see a deterioration. It would just neutral out. And then one could get a little bit more sophisticated in one's argument and say, all right, we should not have just directly deployed what we saw was performing well in offline into our production. We should have perhaps done an A/B test. All right, let's say we did do an A/B test. We do again would see something along the same lines as what we saw if we deployed it in real world, which is an initial bump, a novelty effect that goes away in a little while. Now, one question one could argue or one could think of is there is a subtle difference here. It is not subtle to the practitioners. There is a difference between the goal metric that you're interested in and what the objective is that you're trained your machine learning models to. The objective that you train your machine learning model is something like predicting, am I going to click on this advertisement, or am I going to watch this video? The goal metric that you're interested in is not so much whether individuals watch those videos or not, but maybe an aggregate that says, overall, is the count of sessions or the time that people spend on our platform increasing. So there could be a little bit of a difference between the individual action versus the goal metric. So one could ask the question, why can we not directly move the goal metric, right? And this is what we say. There's a difference between what is commonly perceived and seen from a distance versus what is trained by the machinery to be learned. Hopefully, our hope here is that distance between the metric of interest for the team or the company or the organization versus the objective that the machine learning model is built on can be bridged by adequate data science analysis and somehow approximate that. We may have multiple objectives that a machine learning model needs to learn so that in aggregate they behave closer to what the company's goal metrics would be. All right, that is along the lines of goal metric contributive user action. Just tapping into the right kind of objective functions in these machine learning models so that your A/B tests start showing positive improvements. That's one possible remediation to that distinction being missed. Another item that I want to bring out here, and this is particularly relevant for online services, something along the lines of a social media network, or something along the lines of a YouTube, right? A content recommender system. If you look in here, the very first thing that happens is there's an impression of an app, impression by an app onto the user's device, right? At that specific point, there is the decision to be made, what advertisement or what content is it that I'm going to show. Let's say we do show something out to the user. The user has a delayed reaction to that. They may choose to click or not click. Now, these clicks are obviously easily labelable in the sense that you immediately see a click and you can label them as a 1, let's say. But what about the no clicks, right? There is no distinct identifier that tells us that this label was this advertisement, this content was never clicked on, right? In order to get that correctly engineered, what we typically do is we enforce thresholds, time thresholds that says if the person doesn't click in 24 hours or 48 hours or so, we're going to label it to a 0 and so on. But that obviously leads to biased sampling of biased gathering of data and so on, because who should say whether it should be 24 hours versus 25 hours, right? So that obviously leads to data hygiene, which also has a bearing on what we call partial feedback. Anyway, I was just giving you a sampling of some of the thinking traps that we fall into. Now I'm just going to give you a slide that contains various questions that we peripherally spoke about previously. One question in here that I would like to bring our attention to is the one that's the fourth one, which is features could be null due to data service interruptions, in the sense that at the time of gathering your training data, you may have tons of features that may look nice and pretty as if we have been given clean, sane data, sanitized data. But in real life, at the time of predicting, at the time of serving, we actually encountered quite a few nulls, simply because that's the reality of services. When you are attempting to fetch features, quite a few of them could be null. So that bullet point essentially is to highlight the fact that there is a gross complexity misestimation in our perception of what machine learning entails. And specifically in interactive settings, such as in online services, where you go out and purchase things, or where you go out and interact with social media network or YouTube-like content. As we previously mentioned, we could have partial feedback, and we also have delayed rewards. And one thing to note about partial feedback is, let's assume that we are providing news service. We are providing digital news content to viewers. So a young adult may be preferentially shown content about sports, let's say, whereas a non-young adult might be shown is a content about politics. Now, what this leads to is that since we have not sampled or shown enough of young adults not sports content, but news content, any feedback that we get is biased, and vice versa for the non-young adults, in the sense that we are always not sufficiently exposing all subsegments of users to all possible treatments. So that's just a few seconds of blurb on what partial feedback is. But in interactive settings, we also the goal there is to essentially find the best policy that maps context to actions. That means you want to find the best mapping of context. In here means that it's a user at a particular device at a particular time of the day. What's the specific advertisement to be shown, or what's the specific content to be shown? And discovering that is the goal of the machinery in an interactive setting. This is a little bit different from a supervised learning setting, but the essence of all these is to recognize that there are complexities that we misestimate. Now here, having said all these, I'm going to show you a quick pipeline of what what's involved in embedding. We have taken out a bunch of things in here just to show the events that flow through as machine learning is thought of in a system. Initially, there is an impression that, so this is talking about a contemporary application. The content is impressed on the device, then the user, let's say, performs certain things, but before the user takes specific actions, you log the features as to what the user is, where the user is, what the location of the user is, and tons of other features. And then, as a delayed reward, you log the labels. All right, that's the user clicked on the ad or not. And then eventually we collect them all together, correlate them, and then off on the side, although we have shown an arrow in there, off on the side we do the training of the ML model. And then when we plug in the real ML model into the system, this is what happens. We stick the ML model up there so that even at the time of impression or even before impression, we ask the ML model what is the content that needs to be shown. Right? This is the general setup that happens. Now, when I ask the question, having shown these thinking traps and shown a little bit of the sketch of what the flow and the events are that a typical ML system would entail, let's take a look at this survey once again and see what the responses are like. If you could entertain me and bring up your phones and respond. This is a new survey, please. Yeah. Okay. All right. Let's move on. I think we have comparable numbers of both. Okay. Great. Right now, we're going to quickly talk about a few structures and perspectives that may be helpful, so that we have a little bit more of a detailed idea of how and what machine learning entails, or introducing machine learning into applications entail. So what's one of the things we could quickly do? Well, we could enlist a bunch of questionnaire to be asked even before we take on the burden of sticking in machine learning systems into an application. So again, this is just a checklist of questions one could ask. This is, by the way, a checklist of questions one could ask if one were to build a ML system from scratch, right? Or you could use the same thing to also apply an ML system to an existing application. So now I'm not going to read through all of these. A few things here that would be of interest to folks would be something along the lines of modeling, right? What kind of modeling are we doing? What is also of interest, which is typically missed, is the last item, which is serving and monitoring. How do we serve these models, and how do we continuously update these models, right? That's nice, but where do we go from here, right? So there's a beautiful paper by Google on this, which is to recognize there are a few phases of machine learning deployment, which is starts off with before ML. Take a look at an application before ML, and then there's the phase where you actually apply the first model, and then you do the subsequent ML engineering. That is perhaps a second or third version of the model, and then you go into a later stage where you have slowed growth and hardly any effect or gains are realized unless you actually are able to make tremendous changes to the machine learning model itself, right? Typically, some of the major wins are found in the first model and the second or third models, or at least the larger milestones and larger chunks of wins in terms of engagement are to be found there. Subsequently, we go into a slowed growth phase. And here, what I want to highlight is the fact that machine learning is the high interest credit card of technical debt. So how many of us know what is technical debt? Great. So very quickly, it is technical debt can be summarized as the cost of suboptimal choices made during the life cycle of a product development or product engineering. And these suboptimal choices are not made whimsically. They are made simply because they are perhaps the most expedient way to get a product feature out or to meet a deadline and so on. In the case of machine learning, the technical debt items are much more complicated than regular code technical debt. One item in here of particular importance is that data dependencies. What we do essentially doing by bringing in machine learning is we are bringing in data dependencies into our system. So the choice of whether to show the user a red button or a red text versus a blue button or a blue text is made now by the data. So those dependencies are actually get learned by a machine learning system and brought into the code. And those dependencies can change over time. And not just that, it's not easy to troubleshoot and debug them over the course of an application. The third item in there, the system level spaghetti, has to do with the amount of glue code, that is, the amount of machine learning supporting code that's required to make an application capable of using machine learning systems. There's a tremendous amount of code that goes in if we use libraries off the shelf. If there's one takeaway from this entire talk, that might be right there, the acronym CACE, which is change anything, changes everything. Specifically with applications that are equipped with machine learning models, what one would find is that if you change the distribution of one particular feature, it changes or makes ineffective your existing machine learning model, and that requires us to train and build a model over again. It doesn't have to be from scratch, but it requires us to relearn the dependencies between the features. So now that we go into the third part of the talk, where we actually show an example of how one can possibly remediate and think through some of these traps way ahead of time and show an engineered solution. This solution is based on work by Microsoft, and there are portions of it that are applicable to what we call contextual decision situations, which is an online setting where you are on a platform like YouTube, and there is repeated interaction, either engaging or not engaging with the content. And I think this is perhaps of more interest than maybe a supervised learning setting. So this is a decision service. This is a system for contextual decision making. There is repeated interaction of a user with a particular application, and the act of interacting with that application changes subsequent choices given to the user. There are 4 abstractions here of interest. One is explore, log, learn, and deploy. These abstractions are now here we actually show how it is deployed out. These abstractions allow us to clearly separate out various phases, if you want to call it phases, of the user's interaction with the application. So application way out on the left side, the app now has a direct communication to explore. This is the point at which the app is requesting the ML machinery to give us a content, right? How do we make that choice? At this point, we call it explore simply because it's not handing out the best choice at that point. There is a little bit of an exploration happening in addition perhaps to exploitation. So those of you familiar with reinforcement learning may know that exploration, exploitation, contention, or the different motivations behind that. And that happens in that phase. So a policy that handles hands out a response back gives you a choice of what is the content that needs to be shown to the specific user. And in the act of doing that, although we have notated a box way down in the bottom left-hand corner as feature generator, it's all pervasive and available across the board to all components or all abstractions here. So the question of what do I show Vikram, who is on the app right now, what content do I show, requires features to be generated at that point in time. So that is the one way to think of that is a compression of all the existing data that we know about the history of this person's interaction with the app, and maybe more, and their location, the day and time, and so on and so forth. right? And that compressed data is available to us, feature is generated for the machinery to make a decision, for the policy to give out a particular choice. And subsequent to that, perhaps a few minutes down the line, or a few seconds down the line, or a few days down the line, the system receives a reward from the app. At that point, there is a correlation between what was generated and what this person's action was, and the two are correlated and allowed they are joined together, which allows us to do an online learning. And online learning essentially means that the machine learning model is changing and updating its weights or parameters based on that one sample of interaction that we just saw. Of course, there are learning rate decay and things of that nature that we apply so that this one instance doesn't shift the machine learning model much, further out into undesirable territories. But that's what you do. And then if we have passed sufficient, or we have gathered sufficient amount of data, there is also the choice of an offline learning, which eventually allows us to deploy a newer model into the system. If one were to think about machine learning system now as fully entrenched into your application with a life cycle of events that the users would go through and the system would go through, then I think we have a little bit of a more mature perspective of things. Then we quickly see that the burden of bringing in machine learning is not just what we initially thought of as being three distinct phases, and this is much more, a little bit more of engineering involved business. What are the saliencies of that architecture that we saw? First thing is the service abstractions. The service abstractions is what makes it possible for us to clearly delineate them, the log versus the learn, and so on and so forth. Then it allows us, this is the last bullet point, this is set up like this allows us to address non-stationarity, which is the fact that in the real world we hardly ever find stationary data. That means the distribution of the features, they change constantly over time. They're never, the joint distribution is never the same. And that is addressed by virtue of us having the online learner learn as we see examples come through. And some of the other saliencies can be read through in the paper. For those folks who are interested in under the covers, there are certain things that happen to facilitate this setup. One of them is the exploration policy. That's a policy that is handed out and that's making the decision is not the only policy that is being evaluated. And that's possible using inverse propensity score estimators for policies and so on. And I'll give you a reference to the paper at the end. What does that structure that I just showed me entail in terms of code? Of course, this is I'm trivializing this, but highlighting the fact here that these are the signatures that one could have. So there is an object called MLOps, which has specific entry points into each of those phases or in each of those abstractions, explore, log, learn, deploy, and so on. And then in your application that actually uses these ML systems now, we get a little bit more cleaner of a separation between the ML ops versus core app issues or core app logic. Again, it's not completely separated. As soon as we introduced machine learning models into this application now, we would see ML stuff all over the code. But the cleanliness here is in the fact that we have injected, and for those folks who may know of dependency injection, we have injected the dependency into an object called MLOps, and then we are able to isolate our changes specific to machine learning into those calls right there. Without something like this, typically you would find hundreds and hundreds of lines of if-else conditions in your code. in your machine learning code, in your application code, in order to specifically handle conditions of changing variables and parameters and so on. So these are the references that I mentioned. If one were to take a look at some of these and wanted to spend a little bit of time, I would highly recommend the second one. And for those folks who are involved in a contextual setting, which is contextual systems design, the third item as well. And that's about the stuff I wanted to talk about. I want to open it up for questions from anyone.
When you mention A and B testing,
right?
What are an example of how you do that change? What change are you making that are relevant to learning something about the machine learning model?
Right. So let me repeat the question. When you spoke about A/B testing, right?
Yeah.
How do we make changes in an A/B testing?
What does that mean in the context?
Oh, in the context of machine learning, right? So, so the question is, what does A/B testing mean in the context of machine learning, right? So let's assume we developed a model that produces promising results on click-through rates, right? So that means we are able to now predict very accurately whether a person is able to going to click on a particular ad or content. And offline testing showed that. You had a training data, test data, and it showed. What we do in an A/B testing is segment off a portion of users, call them A, and a portion of users, we call them B. And to A, we supply them the original situation, which is no machine learning model, let's say. Into the population or the segment we call B, we subject them to the machine learning model. So you make code changes so that you can distinguish between the two users. So the users who see the flavor B would now see a different behavior in terms of the content that is recommended to them. Whereas the users A would see the traditional content that they would have without the machine learning model. Okay, and the machine learning model is embedded in the call to the users who are exposed to the path B, and that's A/B testing. And what we do is to typically run that for a few weeks to see whether between the two portions of users, do we see a measurable difference in the outcomes of interest for the team, and that's A/B testing.
Do you need to reverse them in case that you have a biased selection of users?
Yeah, that's a good question. So the question is, do we need to reverse the A and B to see whether there is if we have a biased selection of A and B? So the guarantees of the quick response to that is we do not, because the guarantees of the systems that create A/B testing frameworks is that these are randomly chosen people. So the representation of every subsegment in A is equally the same in B as well. So you do not necessarily have to do it. Curtis.
Yeah, so I'm really glad that you brought up the piece on data hygiene, because I feel like that comes up like a lot. And this is more just a question I'm wondering if people in your space are thinking about, like, have you seen people trying to, instead of just modeling a classification, so instead of thinking like, is it 0 or 1, of approaching it as like a time to event type, where like your event is, say, like a click, and so you're thinking of it as like a censorship situation where it's like it's like a continuously ongoing variable. So you're kind of like, because wouldn't that seem like something that also like a stakeholder is interested in? Like not just like, did somebody click on it, but are they clicking on the ad like right away versus like conditional over some longer stretch of time?
Right. So the question is, in the line of in contextual settings, in online settings rather, we are interested not so much in whether the user has clicked on a particular content, but what's the time that someone has taken to click on it. So yes, the short answer is yes. I have seen folks. So here I have posted as or shown it as a classification question. Is it a 0-1? There are organizations who have done something else, which is a time to an event, and that has varying degrees of success as well. One thing I want to mention here is that specifically in online settings, it's a long tail distribution. So that means the number of people who react immediately versus who react after a week or so would be it would be disproportionate. So perhaps modeling that in one model or one section or one single model may not be that beneficial, because now the model is attempting to predict 1 week as well as 1 second as well as 2 weeks. So the output range becomes so wide. So typically what is done in such scenarios is either you break them down into a hierarchical model in which you say, is this person likely to respond within a day or greater? So that's the first level of hierarchy. Then in each one of these hierarchies subsequently, you predict the exact number of days if you wanted to. So that's something I've seen with varying success, and it's not a solved problem. It is still a problem that various vendors have done in approach in different ways.
Great.
Does that?
Oh yeah, absolutely. No, I'm just curious if you'd seen it and things like that, because that's kind of where my mind went, but super helpful.
Yeah. Please.
Yeah, sorry, I don't know how many more questions you could do, but I was wondering about the inverse probability scoring estimator that you have. Can you kind of dive into the under the hood way that you score that, the estimator?
Yeah. Let me try to see if I have a slide that, yeah, this was a slide I created specifically to possibly attempt answering something like this. So let's say so the question is we want to delve into the inverse probability scoring, right? Let's say the context is X, the column X, the action is all those that we recommend, and then there is a probability number, and then there is a delayed reward. And the table 3 I show there is under executing an executing policy called pi1. So let's say we are executing pi1. These are the XARP that we observe. Okay. But we are in the act of gathering this data. One might say, okay, we can only now know how pi1 behaves. But what we're truly saying with IPS is that no, that's not true. We can also evaluate a policy pi3 by looking at those context action pairs which have matching outcome as pi1. So if you look closely, we have C3A0 as the last row, and there is a probability P 0.01 and the reward of 0.96. You can take that row data, which is what we observed, and apply that to estimate what the score for pi3 would be. Of course, there's mathematics to show you that asymptotically, if the number of interactions as it approaches infinity, this is an unbiased estimator of this, meaning this IPS estimator is an unbiased estimator of pi3 as well. Okay, and that's what I attempted showing in this algebraic expression here, down at the last one, right? So pi I can be evaluated by data that has been collected by, say, a policy pi. Okay. Does that answer your question?
Yeah.
Yeah, please.
Again, naive question. When you mentioned the bump, again, for somebody who's looking from the outside looking in, if you run a model, something you would think things will get better. The performance seems to decrease. How does that explain?
Yeah. So the question is, for looking from the outside, one might assume that deploying a model would improve the outcome of interest. Something along the lines of daily active users, for example. But how do we explain deteriorating or maybe even neutral outcomes? So that's a very deep question. It's not a naive question in the sense that is essentially why all these organizations have hundreds and hundreds of engineers look at things like these. A few quick pointers on what may be causing these, not what causes these, is that the act of recommending something changes the distribution of the input that we subsequently see. So when you deploy a machine learning model, and let's say we are interested in sports videos, and then more and more sports videos arrive on our appliance, our device, our behavior changes. So we change as a consequence of the recommendations now adhering more and more to our likes. Because we may be more discriminatory now and saying, I only like videos of this particular player or something. I mean, again, I'm trivializing that. That's one thing. The other thing is that the user behavior changes. So this, and this is related also to the fact, that the data is non-stationary. The distributions that we saw in a model at the time the model was deployed is not the distribution a week later. The distribution of features a week earlier, but when the model was deployed, is not the distribution of features a week later after the model is deployed. So that's why in that decision service that I showed you, there was an explicit online learning block that attempted to address this, which is to say that every interaction, even a single interaction, is possibly able to contribute something to the learning constantly through online learning mechanism.
Now, if you randomize your recommendations, would that help, lessen the impact?
So the question is, if we randomize the recommendations by the machine learning models, would it lessen the? Well, if we randomize the machine learning model predictions or outcomes,
within a subset or something.
right. Well, you are then exploring a particular subspace, right? We would not be able to know specifically, in the sense, what are the ones to be, to be handed out as recommendations. See, random would actually correspond to tossing a coin, right? 50% chance, you would assume, right? But if you say randomized within a subset, I do not know. I think
Let's say books. I get recommendations for books, and if the recommendations were more unusual, that might pique my interest to explore than if they were like more repeated.
Right.
Or more common, like.
Right. So something along the lines of within a genre, you may have. So there are models there are machine learning models that people have explored. Something along the lines of a Gaussian model, right? Gaussian mixture model, where you are now identified as a member of this section of users who like a particular genre, and now we can sample from that genre and then recommend. Yeah, they may help in that setting. Yes. Yeah, but it's a deep question. There's no single answer to that question, in my thinking. Please.
So during the presentation, you emphasized the importance of KPIs, metrics, and things related to that, right? Now that language models are more popular than ever, have you experienced any kind of evaluation of metrics when the output is an actual new text and not like a categorical or numeric output?
Right. So the question is now that, as opposed to what we showed, which is a prediction 0-1, what if the language? What if we're looking at language models? Do I have any experience with the quality of language model outputs? I personally do not have an experience with that. But from what I read and what I gather, there is a specific phase of large language model training called RLHF, or reinforcement learning based on human feedback, and that is precisely attempting to do something along these lines, which is aligning the machine, the LLM output to be more in line with what human beings have previously chosen to be preferential, A versus B. They're given choices, and then the machinery is now coaxed to produce more of what humans have labeled as being more preferred. I do not know whether that answers your question.
Yeah. I mean, still being a human layer in the process, right?
Right, and I think there are some organizations which have tried doing that as well as using another machinery. So you could use a second LLM to do something like that, things like that. Yeah.
Thank you.
Using like a classification, like you were using like label data, like 0, 1 for as your outcome, how do you collect those labeled data, or how do you make sure your labeled data is correct at the first place for your training, for training?
Right. How do we, so the question is, let's say we have a classification setting and we have data that is labeled 0 and 1. How do we really know that the labels 0 really represent 0 and 1 really represents 1?
Or how do we collect those?
How do we collect, right? Of course there is noise in all this data that we collect for sure, right? But if you look at contextual decision settings, usually it's based on events that we have gathered. Like I said, a user has clicked on an ad, user has engaged with a video, things of that nature. There is a user event that is traceable to that particular context. So I think I showed that in one of the slides here, something along the lines of the second bullet point. So we are somehow able to correlate the X, that is the context, and the action that was prescribed, recommended, what was the reward, what is in this case a 1 or a 0 label, and what is the probability of that action originally being recommended. Maybe not, your question is not pertinent to this, but typically the assumption is that we have a reliable way of gathering the data in the machinery that we have built. And you're right, it is conceivable that if we look at something like here, because we have delayed response and reward and so on, it is quite likely that we may not be gathering unbiased and hygienic data. That's possible. Yeah, but the best we can do is build machinery to be able to gather them.
So in the deploy action, the last the Microsoft architecture, that one, yeah. So there was offline learning as well as online learning, right? So how do we tie those two down together?
Right.
In terms of the results when we're about to make it.
That's a good question. So the question is here in the learn abstraction we show two of them. There's an online learner and there's an offline learner, right? How do we tie the two of them? Typically, this is done. An offline learner is learning off of weeks and weeks worth of data, or maybe in months worth of data, and however, the online learner is learning based on every interaction. Right, or maybe a sampling from every, from that interaction that happens in real life. Ideally, you do want to have some metric to compare between the two of them before you choose to say this is the one I'm going to store and deploy subsequently. So there has to be some regime under which that happens, and that regime would involve, okay, what is the frequency and cadence at which you would do that, and so on and so forth. Right. So there is no one point specific answer to that, except that you go through the action of comparing the outcome metrics for both these models.
Okay.
Yeah, does that get to? Okay. Yes, please.
Just in case in the future we're curious about the recommendation system, would you say that that is one of your main topics of expertise?
Yeah.
Okay.
So it's about my personal experience. Yeah. So I think I've worked quite a bit with recommendation systems and ranking systems. Yeah.
Nice. All right.
Great.
Good. Thank you, everybody.
Thank you all.
So the results of the survey. Let me pull up my phone because I saved them there, and they are going to be. So the first survey, the pre-poll survey, 60% of the people said less than 5%. 24% said 5 to 20, and 16 said 20 to 60. The second time around, it was 50, 27, 23. So it shifted around a little bit.
Yes, it did. So what I observed at NYU, where I gave this talk previously, was it was almost bipolar trend after the fact. A lot of people went, almost 50% went to under 5% code is ML, and the rest of the folks went to around 60% is ML code. the question was put out there just so to gauge what people perceive walking in. So in a realistic system, the number of lines of code that are pure ML is typically less than 5%. What makes the bulk of it is the glue code, the supporting code that helps bolster the whole thing up. And that includes libraries that do all sorts of data transformations and feature engineering and so on. So,
in terms of differences between a well-designed setup and one which is full of technical debt, right? How do those percentages work?
I mean, I think well-designed systems, even those, if you look at it very closely, does not have the machine learning related code is very little in comparison to the engineering that requires to feed it the data and so on. So, and again, I can't speak for the first category that you spoke of.
All right.
Thank you.
Thank you very much for the talk. A little round of applause. The 10th anniversary of the New York R Conference. Once they go on sale, tickets are available at rstats.ai and use code nyhackr for a 20% discount because you're members of this meetup. We need a speaker for next month. If anyone has been inspired to give a talk at the next month's meetup, come find me. I'm here now. I'll be at the bar. Otherwise, look out for an email when we're going to announce it, and have a great night.